make sure my microphone's definitely on. Can we turn that down a little bit, Greg? That a little bit better. I'm not deafening everyone. Fantastic. Well, a very warm welcome to the planetarium here at Glasgow Science Centre for our very first hybrid David Elder Lecture, which is delivered in partnership with the university. Microphone's definitely on. Can we turn that down a little bit, Greg? Tentatively trying again. Is that coming through on the speakers? Test, test. Yep. Right, we're giving that another go. So, good evening, attempt number 2, and welcome to the planetarium. Tentatively trying again. Is that coming through on the... Good evening, and welcome to the planetarium here at Glasgow Science Centre for tonight's David Elder Lecture, which is very kindly supported by the Physics Department at the University of Strathclyde. My name is Nina, I'm the planetarium coordinator here, and I will be looking after the live Q&A portion of the event. Very shortly, I'll be introducing our speaker, Professor Martin Hendry, who's joining us from Glasgow University. But before I do, for those of us in the in-house audience, there's a few things I need to tell you in terms of health and safety, which I'm sure you have sorely missed over the last couple of years. So during the lecture, we are going to bring the lights down a bit. It is going to get a little bit harder to see. So from now on, if you could stay in your seats with your masks on over your mouth and your nose, unless you're exempt, we'd appreciate it. If you do need anything during the lecture or you want to leave, please don't be shy. Let myself know. As I said, my name's Nina, and we also have my colleague Veronica up at the back. We can come and assist you, and we'll lead you out one of the doors at the back. During the lecture, we do ask that things like phones, cameras, tablets get switched to silent and get tucked away in a bag or in a pocket. And if anything super exciting, like a fire alarm is to happen, the lights will come on, the microphones will switch off, and we will meet you at the back in our very stylish high-vis waistcoats, and we'll lead you down some stairs and out into that slightly dramatic Glaswegian weather. We are very much hoping that that's not going to happen tonight. If you do have any questions this evening, we would be absolutely delighted to take them. If you're in the audience, just raise your hand, let us know that you'd like to ask something. And if you're on YouTube watching at home from the comfort of your sofa, welcome. If you've got any questions, please do pop them into the YouTube comments box, and Veronica will make sure that they get to me, and I'll make sure that they get to Martin. So without further ado, I'd like to actually introduce Martin now that we got to that stage. So Martin Hendry is a Professor of Gravitational Astrophysics and Cosmology at the University of Glasgow. He's a senior member of the LIGO Scientific Collaboration, the global team of more than 1,400 scientists that made the first ever detection of gravitational waves back in 2015. That was awarded the Nobel Prize for Physics. In 2015, Martin was also awarded the MBE for his services to the public understanding of science, which is partly why he's here tonight, and he's a fellow of the Institute of Physics and the Royal Astronomical Society and the Royal Society of Edinburgh, and we are absolutely delighted to welcome him for this very first in-person David Elder lecture. So thank you so much, Martin.
Good evening, everyone. So it's with great pleasure that I both give the lecture but also take off my mask. It's good to be here giving a face-to-face lecture again after a very long time away from the planetarium, but a warm welcome also to everyone who's watching the stream at home. So I'm here to talk to you tonight about Einstein's universe and to tell you the story of how we have detected gravitational waves, some of the things it's told us about our universe, and the bright future that this exciting new field of astronomy has in store. Now, Einstein has long been a hero of mine. This is a photo of me taken on Einstein's knee, so to speak, at the statue at the National Academy of Sciences in Washington. And I guess for many people, Einstein is an archetypal example of the scientific genius. You know, the lone scientist who works it all out on his blackboard without needing lots of help from anyone else. And there are elements of that which are true about Einstein. He really did make some remarkable leaps of the imagination to help us understand a lot of the modern physics on which our world is founded. But at least the part I'm going to talk about, the detection of gravitational waves, may be founded on Einstein's theories, but the actual discoveries involved thousands of scientists, as we've just heard from Nina, over many decades, working together to develop the technology capable of making this scientific breakthrough. So what exactly are gravitational waves? Well, before we get to that, let's just have a think about gravity itself. So gravity is the force that we probably encounter most often in our everyday lives. You know, quite simply, it's the thing that keeps our feet on the ground. But Einstein developed a new way of thinking about gravity just over 100 years ago. His theory of gravity we call general relativity. And in fact, in Einstein's picture of gravity, we don't think of it as a force at all. The force picture comes really from the work of Isaac Newton several hundred years earlier. And we've all probably heard the story about Newton and the apple falling on his head as it fell from the tree. And that led Newton to develop a picture of gravity involving a force between all massive objects. And this was a remarkable leap forward that helped to propel us to the moon, for example, to understand the dynamics involved in getting a rocket to the moon and back, as well as understanding pretty well how planets orbit stars and stars orbit around their galaxy. But there were certain aspects of Einstein's theory that took us to the next level. There were certain aspects of Newton's theory which Einstein was deeply puzzled and perplexed by. In particular, Einstein's ideas about space and time, which he developed in the early 1900s in his theory of special relativity, challenged some of the concepts that underpinned Newton's theory of gravity. Because according to Einstein, it was a real problem to think of gravity instantaneously acting from one point in space to another. In Einstein's picture of how space and time worked, things like that just weren't possible. So in fact, Einstein imagined gravity as an interaction between massive bodies that travelled at a finite speed. And instead of thinking it as a force between massive bodies, he rethought the whole concept of how gravity works by imagining it as a curving of space and time themselves. Now this got round a very big problem with the Newton picture, in Einstein's view, which was how does gravity, if it is a force, actually get from one point in space to another? How does the force of gravity from the Earth reach the moon to help keep the moon in its orbit round the Earth? So by thinking about gravity as a curving of space and time, what we replace that idea of a force by is a picture that you've maybe seen before, the notion of a stretched rubber sheet, like a trampoline. So if you drop a massive body in a trampoline, the flat surface of the trampoline will curve and bend. And that's what the image behind me is illustrating in a kind of cartoon form. It's far from a perfect analogy, but it gives us some insight into what it means to be close to a massive body and experience that space-time curvature. Just as the moon orbits the Earth, if you rolled a little marble round your trampoline close to that massive body that's producing the curve and bend in the middle, then that marble will follow a curved path, just like the moon follows a curved orbit, a circular orbit around the Earth. So fundamentally, we're thinking of gravity as a property of space and time themselves. Now, Einstein built some of his ideas, many of his ideas, not just on Newton's discoveries about physics, but also those of the Scottish physicist James Clerk Maxwell. And in the mid-1800s, James Clerk Maxwell unified the notions of electricity and magnetism and gave us insight into what we call electromagnetic radiation, otherwise known as light. Now, light comes in a lot of different forms. Light comes in the form of X-rays and gamma rays, all the way across the so-called electromagnetic spectrum to radio waves. And in the middle of that spectrum is the optical light that our eyes are sensitive to, that we can see. And James Clerk Maxwell worked out that light is produced when you have changing electric and magnetic fields. And that fundamental connection between these fields of electricity and magnetism and light waves that are produced by changes in those fields, that helped to set Einstein on his way to develop his theory of space and time that I referred to a few moments ago, special relativity. In 1905, Einstein wrote one of a series of really seminal breakthrough papers about special relativity, and he name-checked James Clerk Maxwell in the very first sentence of that paper. Now, what's all that got to do with gravity? Well, if light is produced by changing electric and magnetic fields, then gravitational waves are produced by changing gravitational fields. So the space-time curvature that we referred to before, thinking of the simplified picture of the stretched rubber sheet like a giant trampoline with the Earth sitting in the middle, if instead we change that cartoon a little bit and we've now got two massive bodies orbiting around each other, well, that trampoline is going to wobble. Space-time is going to be distorted. Its curvature will be changing all the time. And according to Einstein's theory of general relativity, those changing gravitational fields will produce gravitational waves. As I said, analogous to the electromagnetic waves produced by changing electric and magnetic fields. According to Einstein's theory, they should also travel at the speed of light, just like light. The trouble is, they're very hard to detect. And that's kind of built into the theory as well. One way to think about it is like this. Space-time, if we use that analogy of the stretched rubber sheet, is incredibly stiff, way stiffer than any trampoline I've ever jumped up and down on. And that means that the kinds of disturbances in space-time curvature that we need in order to produce gravitational waves, ripples spreading out through the universe that we could possibly measure, those disturbances aren't the kind of thing you could generate in the lab. What we've got to do instead is to use the cosmos itself as our laboratory, to use things like exploding stars or colliding black holes to shake up space-time enough to produce ripples that we might hope to detect. But let's face it, you don't really want two black holes colliding in your back garden. So typically those sources are going to be very far away. And as the space-time ripples spread out through the universe, by the time they reach us, the part of the wave that we detect will be very weak indeed. So the local disturbance in our patch of space-time will be much smaller than the disturbance produced where the black holes themselves are doing the colliding. So if you crank through the numbers, you find that the ripples spreading on this cosmic pond, by the time they reach us, produce changes in our local patch of the universe, roughly about 1,000th the diameter of a proton. That's the subatomic particle in the heart of an atom. Or a more everyday way to think about it is if you take one of the hairs on your head, we're talking about 1 millionth the width of one of those hairs. So how on earth are you going to detect changes in space-time as small as that? Well, the operative phrase is how on earth, because in fact, on Earth, it's extraordinarily difficult to do because there's lots of other sources of disturbance locally that can swamp that tiny, tiny signal that you're trying to detect. But LIGO, I'm wearing my LIGO sweatshirt here, stands for Laser Interferometer Gravitational Wave Observatory. And LIGO has the sensitivity required to detect these space-time ripples. The twin LIGO detectors in the US in Livingston, Louisiana, and Hanford, Washington, are part of a global network of these detectors. I'll talk about the other ones a little later. But the twin LIGO detectors are the most sensitive scientific instruments ever built. And they are capable of detecting these space-time ripples. And just over 6 years ago, we announced the first ever detection of such gravitational waves to global acclaim. So what exactly did we detect and how did we do it? LIGO stands for Laser Interferometer. So what is a laser interferometer? Well, the cartoon shown here is trying to capture some of the basic design principles. What we have is a very long arm and another very long arm that run perpendicular to each other, about 4 kilometers in the case of the LIGO detectors. So those are just long tubes in which a very high vacuum is maintained, because even a stray air molecule could disturb the laser beam enough to swamp the kinds of tiny changes we're trying to detect. And the changes we're looking for are changes in what we call the interference pattern of the two laser beams. So one beam is sent along one arm, the other beam is sent along the other. They bounce off mirrors at the end. In fact, they do that hundreds of times within the cavity of the arms. But eventually the beams are recombined. And what we're looking for is evidence of the passage of a gravitational wave that will stretch and squeeze space and time, changing by that tiny, tiny amount the length of one arm compared with the other. So the distance traveled by the laser beams, in other words. So when we recombine them, what we see is that the laser beams have got out of step with each other. So that produces what we call an interference pattern, hence the name laser interferometer. Now, that's a very shortened description of the basic design principles of LIGO, and I wish I could go into more detail, not least because it's an amazing story of the technology and how it was developed. But if I did all that, there wouldn't be time to get on to all the stuff that we've done with the LIGO detector. So forgive me for zooming on ahead to some of the discoveries themselves. But by all means, if you've got questions about how LIGO operates, I'll do my very best to answer those at the end. But I should acknowledge that in that giant collaboration, there are people with many different areas of expertise. And in fact, this one the design of the instruments is definitely not mine. It is of a number of my colleagues in Glasgow who were the pioneers of this field. I'll say a little more about that in a few minutes. But the area that I know a little more about is the astrophysics of the sources that produce these space-time ripples. Things like black holes and neutron stars that we will talk more about in the remainder of my presentation. But what we see on this slide is another cartoon, and it's another aspect of the story that's in some ways just as important as the instrument design. The technology to produce those super sensitive detectors is very impressive, but you've also got to know what you're looking for. So basically, building on Einstein's theory of general relativity, over recent decades, breakthroughs have been made in our ability to predict the sorts of signals that things like colliding black holes would actually produce. And believe me, solving those equations is not easy. It's done on supercomputers, and without those breakthroughs, the task of detecting gravitational waves would have been that much harder. It wouldn't simply be about having super sensitive detectors if you don't know what kinds of signals you're looking for. So in the lower left there, we see a little cartoon of two black holes colliding. We see the ripples spreading out around them as they merge and become a single black hole. But what the graph is indicating is a kind of cartoon of the space-time distortion that would produce. So it's a wave, but it's got certain characteristics. In fact, we often refer to this as a chirp, because what it shows is increasing frequency. That means that the wave cycles are getting closer together as the black holes get closer together, and also increasing amplitude. That just means the vertical extent of the pattern, which in other words means that space-time is getting shaken up even more. And then when the two black holes merge, things shake for a little bit more, space-time wobbles a little, and then it settles down again. So those three phases are called the in-spiral, when the objects are approaching each other, the merger, and then the ring down as space-time settles down again. So again, let me emphasize, the challenge wasn't just to have super sensitive detectors capable of picking up these tiny changes in space-time curvature, but also understanding the kinds of signals that we're looking for. Now, back before the pandemic, when I was more regularly out giving public outreach talks and schools talks, a good analogy here that I would often employ, and indeed actually had a little workshop that school children could undertake for themselves, was to imagine the situation where you're in a big crowded room, you know, the kind of situation we rarely are in these days, but like a school cafeteria at lunchtime, where it's probably very, very noisy, with lots of people having conversations simultaneously. And in that kind of environment, it might actually be quite hard to even hear what the person on the other side of the table is saying. But if you know roughly what they're talking about, you know, last night's show on TV or the latest movie on Netflix, then you can often fill in the blanks and you can extract that signal from the background noise. So that's really the challenge we have with LIGO. We want to minimize the noise as much as we can, but we also want to understand the signals well enough that even with quite a noisy background, we can pick those signals out. So I mentioned my colleagues in Glasgow who were pioneers on the instrument side. Now time to just give a brief mention to them, because in 2010, the LIGO detectors, which had already been operating for some years, went offline and were upgraded over a period of 5 years to become advanced LIGO. I mentioned that the laser beams bounce off mirrors, and those mirrors are within vacuum tubes, so that the beam is not disturbed by even, you know, the random motions of air molecules therein. But in initial LIGO, they were suspended on steel wires. And that meant that the mirrors still wobbled a little because of the natural motions in the steel wires. So one of the key upgrades that was led by colleagues in Glasgow, with significant contributions as well from other Scottish universities, including Strathclyde University, who are the sponsors for the David Elder series, what those upgrades did was replace the steel wires by incredibly delicate silica fibers, which didn't wobble so much. So what we were basically doing was making the LIGO detectors the quietest place on Earth, where we had the best chance then to pick out those signals coming from the distant cosmos. All the more so because the theoretical work and computational work allowed us to understand those signals better, to know what we were listening for. Now, I say listening for because gravitational waves are not sound waves, but the range of frequencies that LIGO is sensitive to corresponds to frequencies that our ears can hear. So the signals can be turned into sound. In fact, I kind of alluded to that already because I referred to the pattern on the graph a few slides back as a chirp. So that pattern of low frequency getting higher, amplitude increasing, and then fading away is a very characteristic pattern. We call it a chirp. And very soon after the advanced LIGO detectors began operating, here's what we heard. I wonder if we could turn the volume up in that just a little. If only it was that easy to just command the black holes in the universe to be a bit louder. But perhaps we can do it with our video here. In some sense, we don't want to make it too easy, because after all, the whole point of this is that extracting the signal from the noise was hard. But hopefully what you can hear is a low rumble. And then the second time, what we've done is we've artificially increased the frequency to make it somewhat easier to hear the signal. So I'll stop talking for a moment, let you hear it a few more times, and then we'll talk about it. So I'll pause it now. So what we heard initially was the real signal, the low rumble, and it's very hard to hear any structure in that at all. It's really what we just refer to as noise. But when we increase the frequency, which is kind of analogous to what we often do in optical astronomy by having a false color image of a star or a galaxy, then it was perhaps easier to hear, you know, a more high-pitched sound, but then a kind of zhup sound at the end, a rising pattern, which is just that chirp that we referred to. So if we switch to the visuals, what we see is two patterns that have that characteristic behavior as well. We see the frequency increasing, the amplitude increasing to a maximum, and then fading away. So we've got LIGO Hanford in the top and LIGO Livingston down below. This was September 14th, 2015, and it was the first ever direct detection of gravitational waves. The other coloured patterns that you can see above are just a different way of representing it, where the intensity of the colour is indicating the strength of the signal, but we can see the upward sweep in frequency in both cases. So this was mind-blowing. I was at a conference in China at the time, but aware very early, just a few hours after this signal had been detected, that it was likely that this was the real deal. But of course, we had to undergo months and months of painstaking checks before we could be absolutely sure and to be ready to declare this as our first detection. So in fact, it was February the 11th of 2016, nearly 5 months later, before we made that announcement. And here is what our webpage had to say at the time. It was 100 years after Einstein's general relativity had set us on this path towards the discovery of gravitational waves. General relativity predicts these space-time ripples spreading out through the universe, but it was only 100 years later that we had sensitive enough instruments to be able to detect them. So what exactly had we detected? Let's look at that pattern again in a little more detail. We see the LIGO Hanford and Livingston patterns very similar to each other. That was hugely important because these two detectors are 3,000 kilometers apart. So if they were both seeing such a similar pattern, it was much less likely that that was just local disturbances mimicking a gravitational wave signal. And the nature of that pattern fitted the description I gave a few slides back, where we've got the in-spiral phase with the frequency increasing, the cycles getting closer together, the merger, where the amplitude is at its greatest in the vertical direction, and then the ring down where things settle down. So what we were able to do by analysing those patterns was to deduce that the signal had been produced by two colliding black holes more than 1 billion light years away. Now, extracting that kinds of information from these signals is really key because, you know, it's not just about determining that gravitational waves exist. It's about using them and harnessing them to tell us things about the universe. So we want to be able to analyse the signals and work out what they're telling us about the cosmos. So to just explain a little bit more how we do that, I'm going to use a short video clip made by one of my LIGO colleagues. This is Laura Nuttall, who's an astrophysicist at the University of Portsmouth. So I'll hand over to Laura just for a few seconds in this little cartoon clip to talk about how we extract the data from these signals.
The full wave signals was detected by LIGO. By comparing the signal to the predicted signal, scientists were able to find out more about the origin of the gravitational waves. To determine the mass of the black holes and their distance, we can compare with theoretical models. The parameters of the model are adjusted until the predicted signal matches up to the data. The closer the black holes, the larger the amplitude of the detected signal. The mass of black holes can be changed. The lower the mass, the higher the frequency.
So we'll come back to some of those ideas as we go along, but the essential points are that the nature of the signal, the pattern, gives us information about the objects that produced it. So we can work out the masses and indeed the distance of the black holes that produced this signal. The distance, I mentioned already, more than 1 billion light years away. That means that we're looking at something that happened a long time ago in a galaxy far, far away. So here's, you know, a little bit Hollywood perhaps, but this is informed by the real scientific data. Again, just running with this metaphor of the stretched rubber sheet, we're seeing now the effect that the merger of these black holes has on that rubber sheet. In some sense, it ruptures it. It causes a break in space-time that produces this burst of gravitational waves, and then space-time reorganizes itself now to only have one dimple, one black hole after the black holes have merged. Now, it's very possible that all of this happened without any light whatsoever being given off, just gravitational waves. We'll come back to that point in a moment. But that means, in a very real sense, we're probing the dark side of the universe. Now, between that and a long time ago in a galaxy far, far away, you're maybe thinking we're talking about something to do with this chap. Now, I think it was Darth Vader that once said you should never underestimate the power of the dark side of the universe. And let's illustrate just how true that was by thinking about our gravitational wave signal. So the burst of gravitational waves lasted about 1/3 of a second. There were gravitational waves being emitted all the time for maybe millions of years before as the black holes got closer and closer. But it was only those final few cycles just before they merged that were strong enough for LIGO to detect them. And during that time, about 3 times the mass of the sun was converted into gravitational wave energy. Now that's about 6 million kilograms. And we can work out what energy that corresponds to using Einstein's famous E equals mc² formula, where c is the speed of light, 300 million meters per second. So that's a heck of a lot of energy released in the form of gravitational waves. And if we work out what the power is, that's energy divided by time, remember it's all released in about 1/3 of a second, it turns out to be about 50 times the light power of every single star in every galaxy in the entire universe. So you really should never underestimate the power of the dark side of the universe. Now, the light in stars is pumped out for millions or billions of years, whereas in the case of the gravitational wave power, it was all released in this final cataclysm as the black holes collided. But it's a clear illustration of how much energy there is trapped in the curvature of space-time. Remember I said that space-time is incredibly stiff, so that's why you need things like black holes colliding to release some of that space-time energy. Now, as Nina was kind enough to mention, this was awarded the 2017 Nobel Prize, the discovery of gravitational waves, to 3 of my senior LIGO colleagues. But there's still a lot more to talk about in the intervening 6 years, so I'd better get a move on so I don't overrun. Our next important date is August the 1st, 2017. That's when the 3rd ground-based detector began operations in its advanced configuration, more sensitive. This is called Virgo. It's in the fields close to Pisa in Tuscany, and the arms are 3 kilometers long. Now, having 3 detectors was really useful because with only 2, you can tell pretty well how far away the gravitational waves are, but not nearly so well which direction on the sky they came from. Roughly speaking, there's a ring of points in the sky which the gravitational waves could have come from. That ring corresponds to points where the time delay between the signal arriving at one detector and the other is the same. So there was a short time delay, I think it was about 7 milliseconds between the arrival of the signal in LIGO Hanford and LIGO Livingston, but that didn't pin down the sky position terribly well. But once you have a 3rd detector, that basically gives you 3 rings, and where those rings intersect, that's where the signal is coming from. So within just a few weeks of Virgo joining our global network, this had paid off. So whereas the first gravitational wave signal, 150914, 14th of September 2015, was only pinpointed on the sky to about 900 square degrees, we observed a black hole merger on August 14th of 2017 that was localized to about 60 square degrees, much smaller patch of sky. Now, why would that be important? Well, if we want to look for a counterpart in light of the gravitational wave signal, then it really helps if you can tell your astronomer friends with optical telescopes and gamma ray telescopes where to look. Nonetheless, we don't think that black holes colliding give off any sort of signal in light. They could do. There are some interesting possibilities there, but certainly not routinely from the actual merger of the black holes themselves. But when 2 neutron stars collide, neutron stars are the somewhat less evil twin of black holes. They're not quite so massive and not quite so destructive, but nonetheless they are very compact, very dense, and when 2 neutron stars orbit closely around each other, boy does that shake up space-time. So it does produce gravitational wave signals. That's what we believed. It was a question of, well, would we see gravitational waves coming from a binary neutron star pair? On August 17th, we did just that. So LIGO and Virgo, and indeed partner astronomers using telescopes all around the world, detected an event both in gravity waves and in electromagnetic waves across the entire spectrum from gamma rays to radio. So what exactly did we see, or maybe I should say, what exactly did we hear? So here is our gravitational wave signal. So that's a chirp, but it lasted for much longer. So that immediately tells us we're talking about masses which are less. Remember Laura's video, that the frequency is dependent on the mass. And then you maybe heard the ping. Well, that's gamma rays. Now, you know, it's a bit hard to represent gamma rays any other way, but that ping was 1.7 seconds later. And that was detected by a gamma ray satellite called Fermi and another one called Integral. And we believe that the gamma rays actually set off 1.7 seconds later. They were produced a little later than the neutron star's gravitational wave signal, but it was kind of triggered by the gravitational wave signal because this is what we call, with stunning originality, a gamma ray burst. 2 neutron stars colliding produces a gamma ray burst. But what was also important is that we could pinpoint the location on the sky because of the 3 detectors really rather well. And what we're zooming in on now is a group of just a few dozen galaxies where, well, we figured that the gravitational waves had to come from one of them. So that was a manageably small number to just, you know, phone up your astronomy friends and say, here's all those galaxies, go take a look. And what we were hoping to see was the aftermath of this gamma ray burst. So that's just an artist's impression of the two neutron stars colliding, producing jets of gamma rays. That's what Fermi and Integral had seen, but not really pinpointed well enough in the sky to pick out an individual galaxy. But then along come the optical telescopes like this one, the Smoke telescope in Chile, and this is a before and after picture. That little galaxy called NGC 4993, nothing very special, but what Smoke found was the aftermath, the remnant of these binary binary neutron stars colliding with each other. And I mentioned that there was a great number of such observatories around the world that saw this event, and that was phenomenal information to have. We had seen for the first time an event in both gravitational waves and in light. So what kind of things did we learn from that? Well, the one that's probably closest to my own heart was the area that I have worked on throughout my whole career, which is, in terms of my job title, the cosmology part, trying to measure the expansion rate of the universe, how fast our universe is expanding. So ideas about that go all the way back, almost to Einstein himself, but first observed by Edwin Hubble, after whom the Space Telescope is named, and building on the theories of Georges Lemaitre. So the cosmic expansion we describe in a number called the Hubble constant, but it's proven notoriously hard to measure precisely. And I've kind of spent my whole career trying to do it better. So what we have now is a new way to measure the Hubble constant. We're not doing it terribly well yet, but what we hope to do in the next few years is to address a really, really puzzling situation that has arisen, whereby two different methods to measure that Hubble constant just don't agree with each other. That's methods using traditional electromagnetic observations. So they're represented in this odd-looking graph by the green and orange vertical bands. They don't overlap, the methods don't agree. So what we're proposing using gravitational waves is a very different way to measure the Hubble constant. And from only a single observation, we can't measure it precisely enough to tell whether the green value is correct or the orange one's correct, or maybe it's a different value altogether. So that's represented by that broad blue curve, which is giving us insight on the most probable value of that Hubble constant. Well, in our case, we just can't really say for sure yet what that is. But because this is a completely different way to do it, it's a very important cross-check on the other traditional methods of estimating the Hubble constant, which are in violent disagreement with each other. So in my final short part of the talk, I just want to bring you fully up to date. So I've talked about 2015 and 2017, what's been happening since then. Well, in December 2018, by that time we'd accumulated 11 gravitational wave detections. So in fact, we put out lots of social media about how our catalogue goes up to 11, and you know, all the fans that knew the reference saw the funny side. But what that included was 10 binary black hole mergers and the binary neutron star merger that we talked about just a few minutes before. So our family of black hole and neutron star detections, we kind of represented it in this family portrait here, masses in the stellar graveyard. So what the blue circles are showing is black holes merging to become bigger black holes. Again, if we showed them as black circles, you wouldn't see them. And then down below, there's objects that we've observed and inferred indirectly using electromagnetic observations. So that was the state of play in December 2018. And then in April 2019, we began a new observing run, and we had upgraded the detectors a bit more. We'd made them even more sensitive. And we started on April 1st, maybe not the best date to choose, but we were ready to start listening to the universe again. And we were doing things a little differently by then, because we wanted to share the information about candidate events as quickly as possible, so that as many telescopes as possible could look at the sky in case there was an electromagnetic counterpart. So, well, we put out a public alerts system, mainly aimed at professional astronomers, but lots of other people would follow our alerts too. And in fact, our colleagues in the Birmingham University group, they put together a nice app called Chirp so that you could be alerted when a candidate event had been detected. So this was our third observing run. The first two had borne much fruit, including that binary neutron star event that we talked about. But the rate at which we were detecting events was now really starting to climb. So 03, the third observing run, there were two halves, but the second half ended in March 2020, a little prematurely because of COVID, but by that time, we'd accumulated 90 gravitational wave detections. So in November of this year, November of last year, of course, November of this year hasn't happened yet, November 2021, we published a catalogue of events, those 90 detections through 01, 02, and 03. It took us quite some time from the end of the run in March 2020 to double check that we'd got everything right and to publish all the papers. So that's kind of where things currently sit. We've got this growing family of gravitational wave detected events. We've got our family portrait really now dwarfing the number of black holes that have been inferred indirectly from electromagnetic observations. We can now detect lots of them directly, and boy, it's quite a portrait. And several of these 03 events were kind of special, and we talked about them in standalone scientific papers or press conferences and press releases and so on. So let me just wrap things up by mentioning a couple of those. So for example, we observed in April 2019 an event where one black hole was a lot bigger than the other black hole. And that causes a pattern of space-time distortion, which is much more elaborate. It's a bit like having harmonics on a sound pattern where you've got extra structure in the sound signal. So that was a really interesting example, and just a few months later, we had another one very much like that, where this time the more massive object, definitely a black hole, was perhaps as much as 9 times more massive than the less massive one. So much so that we didn't actually know if the less massive one was a black hole or a neutron star. It was either the least massive black hole we'd ever seen or the most massive neutron star we'd ever seen. Now, because we didn't see any light associated with it, then it's really, frankly, quite hard to tell. But more on that in a moment. Just before we get on to that, there's another one worth mentioning, which is 1905-21, 21st of May 2019, and this was the most massive black hole merger that we'd seen to that point. So much so that it's what we call an intermediate mass black hole, more than 100 times the mass of our sun. And that's actually sufficiently high that it's a little bit surprising that it exists at all. In particular, it doesn't seem likely that it's been produced by the collapse of a massive star, leaving behind a pair of black holes that merge to become more than 100 times the mass of the sun. So it's possible that what we're seeing here was the end of a kind of hierarchical series of black holes merging. Now, if that's the case, that could have quite important implications for how supermassive black holes form. Those are believed to be lurking at the hearts of almost all galaxies, and it's very possible that they are built up from some of these smaller black holes that we are now directly detecting as they merge together. Now, supermassive black holes will be a major target for a space mission called LISA that's going to fly in the mid-2030s and will detect gravitational waves coming from the mergers of supermassive black holes. But perhaps in the meantime, we can get clues about how those might form by studying these intermediate mass black holes. So the final example of interesting events that we've detected in our third observing run is this one here. This is where we definitively believe we have detected a pair comprising one black hole and one neutron star. This was in January 2020, and we announced the results in summer of last year. And in fact, we announced the detection of 2 such examples. So, you wait 100 years for one to come along, and then the second one comes along 10 days later. So what we see on the right here are some computer simulations of what it might look like when a black hole and a neutron star collide together. And we'll just let these play out, because what we're going to see in the top one, we'll zoom in. There you can see in the top left panel, the neutron star is orange, the black hole is black. And what will happen there is that the neutron star is just going to get gobbled up, pretty much whole, by the black hole. There it's gone. Whereas in the lower one, let's just run the lower one again, because that's a little shorter anyway. For some reason it's not. There we are. What we can see in this case is that the neutron star is getting distorted and torn apart rather more slowly, such that a lot of matter is spread out around the black hole before the heart of the neutron star is gobbled up. So the events that we saw were not like that second one. We didn't see any accompanying electromagnetic radiation, such as you might expect to get if the neutron star is being torn apart rather gruesomely and slowly. Instead, the black holes seem to be swallowing the neutron stars whole. So as I like to put it, what we seem to have is a situation where the neutron stars are being gobbled rather more like Pac-Man than Cookie Monster. The black hole is not a messy eater. Instead, it's swallowing the neutron star whole. Now, it could be there'll be other examples we see where there is some matter strewn around as the black hole gobbles up the neutron star, and then we'll have a much better chance of seeing an electromagnetic counterpart. So that's pretty much where we are. There's exciting times ahead because our next observing run is set to begin in December of 2022. But we've seen 90 detections so far. We're beginning to learn interesting things about the cosmic expansion rate, about the nature of black holes and neutron stars, and how one might feed on the other. And frankly, this exciting new field of astronomy in only 6 years has opened up a whole new window in the universe. And we believe it has a very interesting and exciting future. So thank you very much for coming to this lecture. And I hope, like me, that you have found the opportunity to return to the planetarium in person a real delight. I look forward to coming again and seeing the stars projected onto the planetarium. But the next time you look up at those stars, whether the simulated ones in here or the real ones outside, just think of all those black holes and neutron stars lurking out there, waiting to send their cosmic ripples spreading through the universe. Thank you very much.
But I think we've got the slight technical issues sorted. So I'm going to be the voice of our viewers on YouTube. So we do have a couple of questions that have come in, but of course anyone in the audience, if you've got a question, please do pop your hand up. We'd be delighted to take your question. So we can start with one from Peter Crilly, who's asked on YouTube, do gravitational waves interfere with each other?
In principle, they can. You maybe remember that in earlier parts of the talk, I referred to space-time being incredibly stiff. So that means that the tendency for gravitational waves to interact with other gravitational waves is rather more limited than you would get, for example, with radio waves or with light waves. But in principle, it could happen. So in fact, one of the areas that I'm working on with colleagues around the world is the possibility that in the future, we might see some of those interference effects. We might see diffractive effects, analogous to what one sees with water waves or light waves, but imprinted on the gravitational wave signals. We think it would require extremely unusual environments for that to happen. Like, for example, if you have two black holes colliding, the gravitational waves spread out through the universe, but they happen to pass another black hole on the way, then that might produce the kinds of distortions that Peter is referring to. So we haven't seen it yet, but we're absolutely on the lookout for it.
Brilliant, thank you. Anyone in the audience wants to give us a wave? Yes. Martin, if you wouldn't mind repeating the question back, just so that folk at home know what's been asked.
Yeah, that's a great question. So the question is about whether there could be a background of gravitational waves left over from the Big Bang. We absolutely think there is. In fact, we have very good indirect evidence for it. And it's in something that we call the cosmic background radiation. So the pattern of temperature variations that we see in the cosmic background radiation is consistent with the theoretical predictions of a theory called inflation that says the universe underwent very rapid expansion in its earliest moments. And it's pretty hard to have that inflationary expansion without having some gravitational waves being produced. So how would we detect those? Well, you wouldn't use LIGO to do it. And the reason is they're coming from so far back in the early history of the universe that they've been stretched by the expansion of the universe a lot more than the gravitational waves we're detecting with LIGO. And that means their wavelength is much too long to be detected by our detectors. What you would need basically is something that's sensitive to much longer wavelengths. And the LISA mission that I mentioned, it's going to be 3 spacecraft several million kilometers apart. So, maybe we've got a chance to pick something up with them. But there's another neat way you can do it, which is again with that cosmic background radiation. But this time, instead of measuring the temperature of that, what you do is measure something we call the polarization, which is the tendency for the radiation to kind of emit in a particular direction compared with others. Think what it would look like if you put Polaroid glasses on, looking at sunlight, seeing the sunlight bouncing off the waves. Sometimes it will be bright, sometimes it won't as you turn the glasses around. So several years ago, back in 2014, if I recall, there was a lot of publicity about an instrument based at the South Pole called BICEP-2 that was trying to measure the polarization of the cosmic background radiation and claimed that it had done. But it turned out that the measurement, which is an incredibly difficult one to make precisely, maybe they did pick up something, but it could also be explained by other effects, by the effects of dust in our galaxy. So the initial publicity kind of died away. But I think we do stand a good chance in the coming years, maybe sometime later this decade, with more sensitive versions of that BICEP-2 experiment to pick up these polarizations of the cosmic background radiation, which would be a very clear indication of gravitational waves from the Big Bang. So it's a case of just kind of watch this space, or watch this space-time. Sure, well, so what might that tell us about the Big Bang that we don't already know? Well, I mean, there's a lot we don't know about the Big Bang, so it's always good to have an independent kind of cross-check on what we think we know. So when I referred to that period of rapid expansion called inflation, it seems to fit what we observe very well, but this would be a nice kind of hard prediction, clear prediction of inflation that it would kind of be hard to generate in another way. So I'm old enough now that I remember when the cosmic background radiation, well, not when it was first detected, that was before I was born, but only just. And in the late 1980s, we had a big leap forward because we couldn't just tell it was there, we could make kind of maps of it across the sky. And a lot of people argued that maybe those maps were kind of contaminated by stuff in our galaxy. So that's a big concern for the polarization as well. I mean, that's what was the problem with BICEP-2, because the contamination was coming from our galaxy and they hadn't detected anything after all. But with more sensitive versions of that instrument, it should be possible to kind of characterize the properties of that background radiation in such a way that it really kind of nails down certain aspects of inflation models and helps us to understand a little better what was really going on in those earliest moments after the Big Bang. So, thank you, great questions. So sort of quite a long answer, but there was a lot to unpack there. Thank you.
When you're talking about the beginning of the universe, there often is quite a lot to get through. So Derek Young, who's watching on YouTube, has asked that the LIGO installations are complex, and as was CERN, for improving our knowledge of particle physics. Will physics typically need bigger, more expensive infrastructure than other scientific disciplines?
I guess it probably does. I mean, it's hard for me to judge that. I guess there's other areas of science that require pretty big kit as well, and certainly a lot of infrastructure, maybe even human infrastructure, something like the vaccine program that we've seen in the last 2 years. Now, can I really claim that detecting gravitational waves has been as important for the world as finding a COVID vaccine? Well, clearly not. But the advantage, at least that astrophysics has, is that it often leads to a lot of useful spin-off technology as well. So I've always been a staunch defender of the idea that we should do physics anyway because we're curious and we want to understand the universe. But the corollary that it leads to lots of useful spin-offs is very helpful. So let me mention, for example, Stuart Reid, who's Professor in Biomedical Sciences at Strathclyde University, and formerly one of our staff members and postdocs. And Stuart has developed some amazing spin-outs that use our precision control technology, the fact that we can control the mirrors and make sure that they're just the right distance apart so we're as sensitive as we can be. Well, he's applying that same control technology to stimulate the growth of embryonic stem cells. In fact, it was featured on BBC Scotland some years ago, and it was described as giving stem cells a nano-kicking, because what you're doing is stimulating them, but by incredibly small amounts, nanometers, billionths of a meter, but enough in just the right way to make them grow faster. So that's an example of spin-out technology that might, at first glance, seem nothing to do with gravitational waves and black holes, but is leading to really important medical science breakthroughs.
Thank you. If anyone in the room has a question, Yep, I've got one up at the back.
Absolutely. So when let me repeat the question. When the black hole eats the neutron star, what effect does that have on the signal, on the mass of the remnant? So indeed, that applies when you've got two black holes colliding as well. So one of the ways that we can learn whether Einstein's theory is the correct one is by looking at our ability to measure the mass of what's left behind and compare that with what relativity predicts that ought to be. Now, it doesn't predict it's just the sum of the two masses you start with, because some of the mass gets turned into gravitational wave energy. Remember my example with Darth Vader. So you've got to be careful how you do the sums, but we can now routinely, with these 90 events, or at least a sizable fraction of them, we can analyze the data to get the initial masses, the final mass, and see whether the final mass that we measure sort of tallies up with how much energy was released, that's converting mass into energy, and also what relativity says the final mass ought to be. And one of the papers we published in November alongside the big catalogue was exactly that analysis. It was to see whether our gravitational waves matched the expectations of Einstein's theory. And so far, Einstein's theory basically has passed every test we've flung at it with flying colours. But we're not in the business of proving Einstein right. If anything, we're trying to prove him wrong. We're trying to find chinks in the armour of gravitational waves and general relativity by seeing if the theory can be kind of stress tested. And that's why, there's lots more to do.
I'm afraid I think we are just about out of time. So just to finish, I wanted to say an enormous thank you to Martin for joining us back in the planetarium after quite a long absence. I'd also like to thank our in-house audience. Thank you all so much for battling traffic and some slightly dramatic weather to be here. And also an enormous thank you to the people joining us at home. Thank you all so much for your questions. We're so glad you could join us tonight. Thank you all so much for coming.